All right, well, let's just talk briefly about this exam. Hello, everyone. I'm sure you can get together and talk to each other about, how things went, go over the exam. Let's just talk about the data first, take a look at it. The exam 1 average was 76.1 with a standard deviation of 20. 20 is a very normal standard deviation. Just says how far apart the grades are. And so, everyone was within about 20 points of 76. And so the smaller standard deviation, the more clumped together y'all are. You're all kind of on the same page. All right, so exam 2, the average was significantly lower. I kind of told you that exam 2 is usually historically more difficult. And I think the average indicates that. And then not only that, but our standard deviation was pretty large. Now this chart, I like looking at this little chart here because the orange indicates the grades from exam 2, and they're in the order from highest to lowest. So we have the highest score on exam 2 was 100. So there was a perfect test out there. And then there's, you can see the kind of taper off here. But then you have exam 1. So what that student did on exam 1 is in blue. So you can see for the most part, students that did better on exam 1 than exam 2, right? I mean, can you see that from that graph? There actually were a few students that did better on exam 2 than exam 1. So I'm not sure if that's a change in study habits or whatever that is, but that's a good thing, right? Would you say? But I also kind of see from this that certain students who struggled on exam 1, were also still in the category where they struggled on exam 2. So I would be concerned if both exams were difficult for you, right? I'd be concerned about that. I do think that this test was a true test. This was a test of what you knew. I mean, it wasn't like an easy test. It was a true test. You had to know a lot of different things to do this test well. All the little things. L'Hopital was in there. Some integrals. You had a cosine 2 theta, so you had to use your identities. So I was kind of, a little bit ambitious, hoping that y'all would do well with it. And then after I graded them, I realized maybe I had pushed a little too hard. So I don't know. But then you have, a category of students that did well. So this is that kind of gray area. Like, how do I, make a perfect test? It's hard to make a perfect test. So with that said, I think I'm going to do something that's going to allow students to improve their grade because, ultimately you want a test to be an indicator of what you know, right? And I believe that some of y'all know more than what you showed me on that test. I think some of you got hung up on the partial fractions, and once you couldn't get past partial fractions, it was over for you. You couldn't do well on that problem because you couldn't do the partial fractions. Or perhaps, I forgot what the test looked like. Here we go. Yeah, on number 1, if you didn't know what to do with that 4 in front of the x squared, that was going to cause trouble. So I want the weekend, if you'd please just allow me the weekend to consider how I'm going to handle it. I'll tell you what my first thought is, though. My first thought is that I'd be willing to replace one problem on the test of your choice. So now hear me out, okay? So let's say you didn't do well on number 1, and you feel like, you know what? I do feel like I understand trigonometric substitution. Then I'm going to allow you to make an appointment with me. So we're going to have to go through that whole thing again where you have to come into my office. And what you're going to do is you're going to come in, I'm going to give you a problem. And you're going to sit there and you're going to do it right there in front of me. So if you can, now I won't make it super hard problem, but it'll be, if it's number 1 you want to replace, I'll do a trig sub problem, right? Understand? And then if it's number 2, then it'll be partial fraction problem, right? And everyone's going to get different problems. So you can't come in and then your buddy's going to, oh, yeah, the number one problem, everyone gets a different problem. So now that's my initial thought. I want the weekend to think about that because that's a lot of time that I have to commit to that. Yes?
What about those persons that did, you said on this that they're pretty bad on the last one?
On the first one?
Yeah.
So if you're in a position where you did bad on the first one, I think what I said to the class was that if you can show good progress, like to me, this is progress right here, right? If you can show some steady progression, then I won't let that first exam cripple you later, all right? But what we're trying to see is an upward trend. Now it's difficult on exam 2 to have an upward trend. It's just a harder test. But I think the next exam students do better on normally. It's usually a better exam. So this is the comparison of A's, B's, C's, D's, and F's. So the blue is exam 1. If you remember from exam 1, we had lots of A's, lots of B's, good amount of C's, a couple of D's, and we had a group of F's. Quite a big shift here in the second exam. You know, we still have some A's, some B's, some C's, but then it's kind of like, got kind of heavy over here, didn't it? Yes? Yeah. So now if you go on Canvas, you know, you can go into your grades and you can like say what if, and you can start typing in different numbers and trying to see what you need. I mean, you can, I think for the most part, most students, most, maybe not all, are still within striking range of at least passing the class. You know, you just need to do well on exam 3 and 4, or exam 3 in the final. And maybe perhaps you could still get a B or, you know, an A. So I would encourage you to go mess with those numbers yourselves and just kind of see where you stand. All right? Any questions? So I guess what I am saying is I do feel like this exam may have been just a little bit too much. I don't know. It's all relative, right? I mean, if I say it's a little too much to the students over here, then, you know, am I watering down the class then? Am I lowering the standard? And then for these students, am I, you know what I'm saying? Like it's, so I try and go off of like the history of, you know, what I've done since I started teaching, you know, and if I go back and I look, I'm just trying to maintain a certain bar, right? Because ultimately you all have to go compete in a university setting, right? And it makes no sense for me to sit here and curve grades and do things to make your grade look great, and then you go and you compete with, you know, with the people that are here, right? And you could walk in, you're like, I had an A in Cal 2 because my professor made me let me retake all my tests and, you know, inflated the grade to give you an A. You know what I'm saying or not? Like at the end of the day, you got to be able to do it, right? So, okay, enough yapping. We will revisit how we're going to handle this test next week. I'm ready to move on. We get to start a new chapter and new ideas. We are done with techniques of integration, and we are now going to do chapter 7, applications of integration. That's chapter 7. Now, I do not believe that there are any handwritten notes or, pre-made notes in Canvas for this chapter. So everything that I do is pretty much going to be on the board. And remember, I'm recording everything, so you can always go back and watch this if you need to, right? So we've been spending a lot of time learning how to integrate, and now we need to see how we can use that to do something, right? So the first section, 7.1, deals with areas between curves. And that's what we're going to start with today. We already know that, I'll just put this on the side here, that this definite integral gives you the area between some function in the x-axis, right? That's what that is. It's the area between f and the x-axis, that definite integral. What I'd like for you to consider is the fact that this is actually the area between two curves. All right? The first curve is f. The second curve is actually the x-axis right here. You could, if you wanted to, call this function g. Now, that function would be a flat line, wouldn't it? And in fact, if it's going through the x-axis, or if it is the x-axis, the actual function itself, you'd call that like g of x equals 0, right? Because 0 would go like that. So this right here is actually this integral. Even though we never looked at it like this before, this is actually the integral f of x minus g of x. All right? That's actually what that is. But because this is 0, we haven't considered it. Does that make sense? So what we're going to do in this section is we're going to take two curves, try and find the area between them, right? So the implication here is that we have more than one curve, right? Curves. So we need to come up with a formula for it. All right, that's what we're going to start with. But I just want you to see that we've already kind of done this, all right? So when I give you the formula, it's going to kind of make sense, I hope. So here we go. Let's develop the formula. And I want to kind of stress to you right now that the most important thing with what I'm about to do is you understanding where the formula is coming from the geometry. Okay? Because as we progress, that's all it's going to be about, is having a problem, understanding the geometry, and creating a formula from the geometry. All right, so let's just see if we can work it out. All right, so let's start here. We're going to go between a and b. So we fix some interval. We have some function up here. Let's say f, goes both directions. But let's just stop it here and here. So we're looking at our f function there, right? Let's say we have some other function. Let's call it g. So here comes g. And I think I'll make g just do this. I'll make g go through that same point over there. How about that? So that's our g function. And I'm interested in the area between the two curves between a and b. So if we were to take a dotted line up through here, dotted line up through there, we are interested in this area in here, right? What is that area? So we clear on the geometry so far? All right. Now, again, this may seem obvious to you, but trust me, we need to understand the basics before we can start like rotating these things and doing all sorts of weird stuff with them. All right, so if I want to know that red area, let's go back to the way Riemann approached it. Riemann did rectangles, right? A bunch of rectangles. So instead of looking at the function all the way down to the x-axis like we did before, let's imagine that we have some rectangle in here like this, right? That's one rectangle. What I could do is put an infinite number of rectangles in here, right? An infinite number. But if I drew just one of them, this would be a good representation of one of those little infinitesimally thin slices in there, right? So if I could somehow add up all of the little rectangles in here, then that would give me the area, yes? All right, so let's see if we can't come up with a formula for that rectangle, a formula for its area. Well, let me draw that rectangle. I'm going to kind of just move it off the graph over here and take a look at it. I've got my x-axis down here. So I'm kind of like just making a copy of it without the graphs in there. How wide is this rectangle? So go back to your formula. Remember how we got this formula from Riemann sums? Do you remember what this represented and this represented? f of x was the height of the function, right? And this was the width, right? That's how wide it was. Y'all agree? Okay, so if I am going to allow myself to imagine an infinite number of rectangles in here, then each one of them is going to have a width that is that little dx, that little infinitesimal width. Do you agree? That's dx. Now, how tall is this rectangle? So now we just need to work with a little bit of geometry here. Well, the distance from here to here, right, isn't it this distance right here? F, that's how tall it is, right? But then take away this lower distance right here. Ah, wow, that's terrible. That was supposed to be a brace. It got away from me there, it got away from me. Okay, so the distance from the bottom, do you all agree with that? Because the bottom of the rectangle is constructed by the bottom of the curve, well, the curve G, right? So that height right there is G. That height right there is F. So this height is the difference between the two, right? It's F take away G. So this height right here, or this distance, the height of our rectangle, is our F function minus our G function. Do you all agree with that? Now, if you like, you don't have to put F and G. You could also have written F of x minus G of x. They're the same thing, right? It's just here I'm leaving out the independent variable, which is x. Here I'm stressing to you what the independent variable is, which is the x. All right? So what is a formula for the area of that rectangle? Give me a formula for that area. What is it? Yeah, it's the height of it times the width of it, which would be this times that, right? So that would be f of x minus g of x, right? But then times dx. I need that in parentheses, though, because if I multiply, this would have to distribute, right? That's the area of one rectangle, yes? I don't want the area of one rectangle. I want to add up all the areas, right? How do we add up an infinite number of rectangles? What do we use? What's the notation we use to let people know that we are going to take the limit as n goes to infinity of the summation of all that crap? What is that really for us? It's the integral sign, right? That's what that integral sign meant. This was the area of one rectangle, and then this adds them all up, an infinite number of them, right? Yeah. So this is the area of one rectangle. If I want the area of the entire region, if I want the area of this whole thing in here, right? That area will be the infinite summation, right, of all of these guys, which is f of x minus g of x dx. Right? So do you see now it's the same formula? Height of rectangle times width. Height of rectangle times width. Add them all up forever, right? All infinitely many of them. But I do need one more thing on that formula. What? The limit of integration. Now the limit of integration, a to b, is telling me, I want you to look at it a little different than you've looked at it before. See, this was one rectangle, right? Yeah. We want to actually have all the rectangles in here. So we want to be able to imagine like sliding that rectangle back and forth, right, to get all of them. And to slide it back and forth, we have to vary the x-coordinate, don't we? And that x-coordinate has to vary between what? A and b. So if we allow ourselves to go from x equals a all the way to x equals b, we will be adding up all those rectangles as we move. So that's what this a to b means. The a to b means sliding that rectangle back and forth. I hope this makes sense. Like I said, the key to the whole thing is for us to understand the geometry. I mean, I could have just walked in here today and said, hey, if we want to find the area, here it is. Here's the formula. There we go. Let's use it. But it's critical for where we're going for you to understand how to create the formulas from the picture. Sure there's no questions? All right. Let's do an example. Okay, first example. I don't like the red. Find area between y equals x squared and y equals 4 minus x squared. Now, I should have pointed this out earlier today and maybe earlier this semester, but I guess I'll tell you now. You're going to have some knowledge of graphing functions to be able to do well with Chapter 7. Like, you're going to need to know basic functions from college algebra and pre-cal, and that will help significantly. Like, if you don't know what those two look like, you're already kind of like a little bit in trouble, all right? Just letting you know that, all right? So, are we comfortable with those? Yes? Okay, so I'm going to draw these first. And when I say draw, that doesn't mean it has to be perfect. It's just a quick sketch of what's happening. So y equals x squared, parabola, right? Opens up. And so this right here is a function. I'm not going to call it f or g or anything, okay? I'm just going to label it. This is y equals x squared. And then the other one, 4 minus x squared, looks like what?
Doesn't it go up like 4 and then upside down?
Yeah, it's an upside down parabola because it's negative x squared, but the 4 in front moves the whole thing up 4. So it's going to look like this. And again, this is just a general sketch. I might have to redraw everything. This is just to get my mind going on, what things look like. So I want the area between those two, right? Does everyone see what we're talking about when we say the area between those two? There's only one region that it could possibly be, and that's everything in here. We want to know what that area is. So to do this, I'm going to, instead of again relying on a formula, I'm going to think about it geometrically. I have a bunch of infinitesimal rectangles that I'm going to want to put in here, right? So I'm going to just draw some arbitrary one. I'm just going to notice I'm not putting it in the center. I just kind of picked some arbitrary point in here, and then just drew a vertical rectangle. Now to the side, I'm going to move that rectangle over here, draw it over here, and then start talking about what the area of that single little sliver rectangle is. So how wide is it? Dx, all right? Because I'm going to let x be changing, right? So this is dx. That's that little change in x. Now the height. So let's see how tall this is. So you have what I'll refer to from now on as a top function and a bottom function, right? What is our top function? This one, I never labeled it. Y equals 4 minus x squared. Right, so this is like the top of that function. So this right here is creating the top edge of that rectangle, isn't it? Yeah. And then the bottom edge is being created by this other function right here, the blue one, right? So the blue one is x squared, and the red one was 4 minus x squared, right? So if I wanted to know this distance, it would be the top one minus the bottom one, wouldn't it? Okay, so let's do that. This distance is going to be the 4 minus x squared, right? It's the top function, minus, I get to play with colors today, minus the x squared, right?
Was this
Question.
mentioned in calculus?
Was what mentioned?
Was this applications of integration mentioned in calculus briefly?
You may have done areas between curves in Cal 1 depending on your professor.
I think we did it, but we were relying on a calculator.
Maybe, yeah.
Are we going to do it without the calculator?
What we're going to do is, like on your homework, you're going to have to do these like by hand the whole way. And I'm going to do a few of these by hand the whole way. But you'll see like when you get to the test is mostly going to be, hey, like find the area between these, set up the integral, but don't evaluate the integral. So like I'll make you set up the integral, but then you don't have to actually work it out.
Yeah, we weren't taught that at all.
Yeah, it's just for saving time on a test. We don't have time to sit here and do them all. Because as you'll see, when we put this integral together, this is an easy integral. And I'll just trust you could do it, right? All right, so look, let's finish this off. We still have some work to do. Can we talk about what the area of this one little sliver would be? Not the whole thing, just this one little sliver. What would its area be? This right here, right? It would be 4 minus x squared, but then all of that times the width of it, which is dx. And we want to integrate that, don't we? To integrate it means add them all up. So the area of the green here, right, the area of this green will be the integral of this, the antiderivative of this. So that's the area of one sliver. That's the area of all of them added up. But I'm missing something here. What am I missing? I'm missing my limits of integration, right? I need to know where this rectangle is supposed to exist. Well, that's supposed to exist from, well, where? We never determined that, did we? So we actually have to go get this now. Where does that region start? Where they intersect, right? And where does it end? Where they intersect. We actually need to figure out what these points are, right? Those are question marks. So how do you find the intersection? How do you find the intersection of two functions? Set them equal to one another, right? So I'm going to do that up here. The intersection will be setting the functions equal to one another. So I set this function equal to this function. Since they're both solved for y, right, then I can just set x squared equal to 4 minus x squared. And you get, this is just algebraically, you can move things around, so I'll move that to the other side. 2x squared equals 4, so x squared equals 2, right? Divide by 2. And then x equals 2 answers, plus or minus root 2. So I take the square root on both sides. So this tells me that they will hit each other when x is either root 2 or negative root 2. So those are our two x values. Negative root 2 here, and then this one is root 2 here. So that gives me my limits of integration, doesn't it? This goes from negative root 2 to root 2. So somebody out there sitting there is thinking this maybe. Could we have just done from 0 to root 2 and doubled the answer? What do you think? Could we have gone from 0 to root 2, just done that integral instead, and then doubled the answer? What do you think? In this case, yes, because of the symmetry of the problem, we could. But in general, you can't. So you could do that, but I mean, you could do this too, and it will give you the answer, right? All right. That's it. So now we would do this integral. If we could do this integral, then we'd have the area. So let's do it. I mean, it's our first example. We may as well just take it the whole way. Now, algebraically, that just becomes integral negative root 2 to root 2, and then what, 4. When you take this, I didn't need the parentheses here, right? I just did it to stress that we had like the top function and minus the bottom function. But when you combine those, what's that? Minus 2x squared? And then do you have any problems integrating that? What do we do to integrate that? You could pull 2 out of the whole integral, but that's just power rule, right? Nothing tricky here, right? No, don't go trying to pull out your sledgehammer to put in a little finishing nail into the wall, okay? All you need to do is power rule on this, all right? So we're going to do, 4x minus 2/3 x cubed evaluated negative root 2 to root 2, right?
So they weren't being multiplied, right?
They were not being multiplied. They were being subtracted. Because remember, where did that subtraction come from? It came from this minus this, right? Nope. subtracted. All right, then once you do that, you plug in the root 2, right? And then you subtract from that negative root 2, and you get some answer. Now, it appears that the answer is going to be something with roots in it, and it's going to be kind of ugly, but we'll just keep going. So I have two things here. So what happens when I plug in root 2 first? Get 4 root 2, right? Minus 2/3. And then root 2 cubed. What's root 2 times root 2 times root 2? It's 2 root 2, right? Root 2 times root 2 times root 2. These two come together, that's a 2. But then you still have a root 2. So I'm going to put times 2 root 2. And then we plug in negative root 2. So we get 4 times negative root 2 minus 2/3. And then when you plug negative root 2 in here and cube it, what do you get? You get negative 2 root 2. Okay, that. I'm going to keep going. All right. I have 4 root 2 minus 4/3 root 2. So I'm just putting those together, right? Like that. That's 4/3. Then these two together are negative, right? But then I'm subtracting. So it's going to become plus 4 root 2. And then when I put these two together, right, like this, that's going to be a negative. Negative and negative is positive. Yeah. And then you have minus. So I'm going to have minus out here, what? Yeah, these two go together. That right there is 4/3 again. So 4/3 root 2. That's rain. Is that rain? It's rain. Okay. They said we were supposed to get a lot of rain today. I was waiting for it. 8 root 2, that's those two together. Minus 8/3 root 2. Equals, one more step. These are both like radicals, right? They're both root 2's. So you look at their coefficients, 8 and 8/3, and you're subtracting. So what's 8? Take away 8/3. You have to get a common denominator there. 16/3. So that minus that, you get 16/3 root 2. That is the exact area underneath, or between those two curves. 16/3 root 2. And you would not want to put that as a decimal. Okay, we want the exact answer, not the approximate answer. What do y'all think? You like the integration? Yeah, the integration's not that bad, right?
It is indeed moist outside.
It is, yes, I can hear that. Nice. All right, let's do another example. Let's find the area between x and cosine x. And x equals 0 and x equals pi over 2. Okay. So now I've thrown some extra stuff in here, haven't I? But let's not freak out about it. There's nothing to freak out about yet. Yet, right? Okay, so do we know what this looks like? Y equals x. Yes, it's just the diagonal. Do we know what y equals cosine x looks like? Yes. Now, do we know what x equals 0 looks like? What is it? It's a line, horizontal or vertical? Vertical line. This is a vertical line. X equals 0 means you go to x equals 0 and you draw a vertical line. So this is a vertical line through x equals 0, and this is a vertical line through pi over 2. All right, so you have to go back in algebra, remember, like, you know, if we write x is a constant, that's a vertical line, y is a constant, is a horizontal line. So let me draw all 4 of these together here. We have this y equals x, right? That's y equals x. Then we have the cosine function, right? Cosine looks like this. And it goes this way forever, right? Something like that. I'm going to run out of colors here. This is the red one. This is the blue one. I've got green, so x equals 0. X equals 0 is the same as what? The y-axis, right? Isn't that the y-axis? So, I don't know. There you go. There's your x equals 0. Let's see any other colors around here. Purple? See if I can get these to go together. No. Let's see. See if that looks purple. No, it doesn't work. Does it look kind of purple? Okay, we'll do that then. Okay, so what? X equals pi over 2. Now, where is that on the graph? Where what? It should be where the cosine function crosses the x-axis, because cosine of pi over 2 is 0. So it's like right there. Now, I kind of have to trust that my picture is pretty good. You know, I might want to break out the calculator, graphing calculator, to help me see that. But that's my x equals pi over 2. Okay? Now, I am trying to find the area of the region between all 4 of these. It has to be between all 4. So look at this region right here. Is that the region? No, because that's the region between cosine, this one, and that one, but it's not. It doesn't have the green one, right? Is it this one? That one? That one? Okay, what's stopping you from continuing to go down forever? Nothing. See, the x-axis isn't part of your boundary, is it? Right? And so this would just continue forever, wouldn't it? It would just like overfill down there. So which region are they talking about here? It would have to be enclosed by these 4, right? So this one right here is enclosed by 3 of them, right? Like these 3. And then this one right here is enclosed by 3 of them. But I need you to see that all the other ones kind of like overfilled. Do y'all see that or not? Like this over here, it's not this, right? Just kind of goes forever that way. Up here, like that, just goes like that. Then what about this up here? Just keeps going forever, right? Those are called unbounded regions. So let's see, over here, no. Over here, it kind of overfills down into here. Right here, keeps going, right? Here, keeps going. So I think, what, these 2, right, would be the ones of interest? Would you agree with that? I mean, we need to at least just see that we have something interesting happening here. Now, I think at this point it would be best for us to get a more accurate graph, because it could be that that doesn't quite look like that. So what I'm going to do is I'm going to go to some graphing utility. And there's different ones out there. There's one called Desmos. Have you all ever heard of that one? Desmos is pretty good. It's just a website you can go to, and you just come over here and you type in different things. So let's go cosine x. There we go. And then what? X. And then I can't really get any vertical lines, right? Let me zoom in on this. That's not very good. Can you all see that over here? Yes? Now, where is pi over 2 on this picture? So what is pi? I think I can change it on here. Let me practice that. I haven't done that. Let's see. X-axis. I think I can do step pi. Yeah, if I just go there and put step pi, it does my pi's. Let's step by pi over 2. Did that work? Yeah. So there's pi over 2, right? So, what do you think? We have the vertical line over here, right? Yeah. Like this. We have a vertical line over here like this. So it's looking like this region, but that region's not bounded by all 4, is it? It's just bounded by 3 of the 4. Then we have this region here, which is bounded by, again, 3 of the 4. But at the end of the day, if we're going to just do this region, wouldn't we need to know this point? Right? Because that would tell us where to stop our integral. We would start it at 0 and end it where? Wherever they hit each other, right? And then you'd go, the next area right here, you'd have to go from there to pi over 2. Agree with that? Like we could split it into 2 integrals, couldn't we? Do y'all see that? And we have a problem though. And that's why I wanted to give you this. Because in the previous one, finding the intersection, wasn't that kind of easy? Like x squared equals 4 minus x squared. Here, to find this point of intersection, what would we have to solve? What is it that we would have to solve? X equals cosine x, right? You'd have to set that. So if I was trying to find for this problem the intersection, I would set x equal to cosine x and try and solve that. And guess what happens here? You can't do it. There's no algebraic way of doing that. There's no like set of steps we can start doing to solve this equation for x. Can't be done.
Can we do like Newton's?
Where'd you hear that from? From Cal 1. That's right. There is a way to do it with Newton's method. So but it's not algebraic. That's an algorithm that we would run on a computer. And what it would do is it would get us close to an answer. As close as we ever wanted it to be, but that's how we would do it. So if I go to Wolfram alpha right now, if I were to do that, you know what, let me get to a new tab here. If I go to Wolfram alpha and I say solve cosine x equals x, it's going to spit an answer out really fast. 0.739, blah, 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 right? But do you see the little squigglies? Okay, that's because it ran Newton's method, or it's using a better algorithm than Newton's method, but similar sort of thing. And it's giving you the result. Now, ooh, exact form? Ooh. Yeah, see, it can't give you an exact form because it's not possible to get an exact form in this case. It can only be approximated with some sort of algorithm. So what am I getting at? What's my point? My point for this problem is that setting up the integral is one thing, all right? That's just one aspect of these problems. What becomes also equally as important is being able to determine where the functions intersect. And if it's a polynomial equal a polynomial, you might have to solve some polynomial equation. Something as simple as x and cosine x, as much as that looks very nice, like you wouldn't mind integrating either one of these, would you? Right? But if we're trying to figure out where they hit each other, now that becomes the bigger issue that we can't handle. So we can handle the integration, we just can't figure out where they intersect. So there's 2 major components for this area between curves now that we have to look at. intersection points along with what we're integrating. Does that make sense? Okay. So what I'm going to do for this problem is I don't want to go through and do this with a decimal. I actually don't, because it's just going to be an approximation and I don't feel like doing it. The point of this was to show us that intersections of functions is not so easy to do sometimes, all right? And that's not going to happen on a test. I'm not going to give you something like this and be like, yeah, good luck with that, Newton's method, right? But it's more to point out that don't take for granted the intersection points. They are just as important in the problem, all right? All right, so let's start with a new example. Let's do something we can integrate or can find intersection points of. And let's go with find area between. I've assigned for you the odd problems out of the section 7.1. So I'm going to do a couple of the even ones here. There you go. Find the area between these. So we have to know what these look like. Right? We have to have some idea of what these look like before we can start doing anything. So let's start with x equals 2. X equals 2, vertical line through 2. Okay, so that should be pretty easy to graph. All right, do we know what a root function looks like? Starts at a point, goes like this, right? Now, where does it start? Let me try and get this picture here. And I don't mind you using your calculators for this, to help you, all right? But on the test, a lot of times I'm going to want you to draw a picture. So where does that root function start? At -2. So it's been shifted to the left by 2. So it starts like this, goes like this, and that is our y equals root x plus 2. Now, x equals 2 was this function like this. And by the way, this stops at a point, right? This root function doesn't continue or anything. It stops there. This is our x equals 2. And then we need y equals 1 over x plus 1. What is that? Let me do this. Let's add one thing in here just to make our lives a little easier. Let's add x equals 0. Let's add the y-axis. Okay, let's add the y-axis in here. Okay, so I'll do that in a different color. We have this line right there. This is x equals 0. All right, I need to have a graph of this. Do you all know what that looks like? You have something weird going on, yes. Where's the weirdness happening? At what value is the weirdness happening? So this is 1, this is 0, this is -1, this is -2. So where's this function undefined? At -1, right? So we actually have an asymptote here at -1. It's a rational function. So you have a vertical asymptote at -1 because you have division by 0. Now, what does it look like? So what happens is you come in from the left and from the right. How could you figure it out? How about just plug a point in? How about plug in 0? If you plug in 0 into that function, where are you? 1. So that, like somewhere around there, that's on my graph, right? Now, what if I plug in 2 onto that function? Where am I? What if I plug in 2, I'm at 1/3. So at 2, I'm at like 1/3. somewhere, let's say around here, right? As I go out to the right, it just keeps getting smaller, doesn't it? And what happens as I get closer to -1? Takes off to infinity. So that graph looks like that. You see it? Now, do you see the region that we're talking about? It's the one that's between all of those, which is this one. Right? It has the root function on top, has the 1 over 1 plus x on the bottom, x equals 0 here, and x equals 2 here. Yes? We want to know the area of that green region. So are y'all okay up to this point? You sure? Okay, so let me just draw an arbitrary little rectangle in here. Here's a little arbitrary little rectangle. And then over here on the side, I'm going to draw that rectangle again, like this. How wide is that rectangle? Dx, right? That's not going to change, right? Now, tell me how tall this thing is. So you need to know what the top function was, and you need to know the bottom function. So we need to know what that was and that one. So what's that top function? It's the root function, right? So the top function is the root of x plus 2, but then you're going to subtract from that this bottom piece. And that bottom piece comes from this curve, right? Which is which function? 1 over 1 plus x, right? That's how tall that rectangle is. This is how wide it is. We want to add all those up, and we want to move that rectangle between where and where? 0 to 2, right? 0 to 2. So I want to go integral 0 to 2, top function, 2 plus x, x plus 2, doesn't matter, minus 1 over 1 plus x dx. Right? And that's it. We grind that out. Let's get the antiderivative. I don't think I'm going to plug the numbers in, but I'm going to at least get the antiderivative. So if I'm taking the antiderivative of this, don't do trig sub, that's not squared. So this is just a basic, this to the 1/2, right? So you can just make that 2/3 x plus 2 to the 3/2. That would be like a little power rule that you're doing on that. And then what's the antiderivative of 1 over 1 plus x? ln. So minus ln of 1 plus x. And then evaluating 0 to 2. So now we plug in 2, we plug in 0, subtract, get the answer. Yes? Notice on this problem we did not have to find where anything intersected. Do you agree? And that's because we were given x is 0 and x is 2. Yes?
So what would have happened if it would have gave us x equals 0?
If we would have not had x equals 0, then we would have had to have found this point right here. Right? Yes? Which would have required us to set these two equal to one another, right? I'm going to say I'm done with this. We would have had to have set root x plus 2 equal to 1 over x plus 1, right? So if I had to solve that, I'd probably square both sides first. So when I square the left, the root goes away. When I square the right, I'd get that, right? And then I'd probably multiply both sides by x plus 1 squared. Like that. That would clear the fractions out. Then I would expand the whole left side out. I would have a cubic polynomial. And then I would hope and pray that someone made this problem so that I could solve that cubic polynomial. And then you would have to go back to algebra and be like, okay, how do we solve like higher degree polynomials. Remember like the rational zero test? And I mean, there's ways to try it. Now, I wouldn't give you this problem. That's why I said let's put x equals 0 in here to make it easier. Because this is probably going to work out very nasty. My guess is that if we did that, we wouldn't be able to solve it.
But this is like this from the homework, this problem.
Yes, but I was looking at, okay, so I'm looking at the problem. They drew the picture for you. So it was easy for you to see these things. Pardon?
Did they give you the intersection?
No, they put in the x is 0. I didn't realize it in the picture. That's all.
I didn't know if there were going to be others to questions.
No. That's not going to come up on the homework. You would not have to solve this type of equation on the homework.
You
So-
said we go as far as setting it up and not solving it.
No, in the homework, you should solve this. I said on the test, we won't have time for you to go through and solve all these. All right, let's look at something else. So what is your general feeling so far? Does this seem a little bit better than what we've been doing, or now are you afraid of graphs? Okay, let's try this. How about finding the area between this? 4x plus y squared equals 12, and x equals y. And that's it. That's all that's given. Well, we have to draw this, right? If we're going to have some idea what's going on here. Okay, we can solve this one for y pretty easily because it's already solved for y, right? So y is x, that's the diagonal, right? But the other one, if we try and solve it for y, aren't we going to have to take a square root?
Yeah.
We are. Let's use that approach just to start this one out. Let's just see what would happen. If we said y squared equals 12 minus 4x, right? Just move the 4x to the other side. Then take the root of that. When we take the root, we have to do plus or minus, right? I don't know. What does that look like? It's actually two functions, isn't it? It's two different functions. So let me try and graph these. Let me do the easy one first. Let's do y equals x. That's this one. Right, that's y equals x. Now, how in the world do I graph that other one?
Does it go right 12 and then up 4? Because anything that's inside the square root, the opposite of it should be, so if it's positive 12, it should go. Did I say right 12, left 12?
How about we do this? I mean, there's different things like shifts that you can look at. How about we just plug in some values of x? Okay, so let's let x be 0, right? Let's let x be 0. If x is 0, don't we get plus and minus root 12? So if x is 0, I'm at plus root 12 and minus root 12. Two different points. Plus root 12, minus root 12, yes?
Yeah.
Okay, what if x is 1? Where would I be? If x is 1, 12 minus 4, I'd be at 8. I'd be positive root 8, negative root 8, right? Which wouldn't be quite as much as root 12. So I'd be like here and then here. Agreed?
Yeah.
And then where would I have like a point down here somewhere?
Yeah.
Where would that happen? At 3, right? At 3, you get 12 minus 12, you get 0, don't you? So at 3, you get this. So what we have is this. We have, it's not that great of a picture, but geez, it's a sideways parabola. Or if you like, you could look at it as two root functions, one pasted to the other one, right? Or you look at it as a parabola opening up sideways, which if you would have thought about that in the very